Hi, and welcome to the next lecture unit in the lecture chapter course of Dimensionality, where I consider various direct examples of machine learning algorithms that we have studied here before or in the Introduction to Machine Learning lecture, and how they break down if we increase dimensionality. So let's start with the simple KNN algorithm. So I'll look at the performance of what happens with KNN if I increase the dimensionality as promised before. So, and hopefully you already I kind of made you aware or pointed you towards a potential source of that problem through the geometric examples that we discussed in the previous lecture unit. So think again of this these various examples with the spheres and the cubes, where I discussed that most of the volume is now contained in the outer regions, like the outer shells of these geometric objects. And that I already claimed there that because of this, distances between points become more and more equal, and because of this, it becomes much harder now either to kind of directly determine the nearest neighbor anymore, because also these these measurements that our distances are based on, these feature measurements, they're not going to be completely exact, right? There's an error component in them, so maybe we cannot even now perfectly determine a nearest neighbor anymore. And if we can, even if we could, we might still want to discuss whether it really now makes sense to kind of interpret that point as a next neighbor anymore, because the distance from that point from a specific point to its next neighbor will have become very, very large. And before I directly demonstrate to you what happens with the performance of the KNN algorithm in high dimensional spaces, let's do some simple calculations first. Again here, with respect to this simple hypercube in a p-dimensional space, where we'll now put a uniform distribution on that hypercube and simply draw 10 to the 4 points from this uniform distribution, and then I will simply calculate for all pairs of points the minimum distance between all pairs of points, the average distance, the maximum distance, and then specifically for KNN, we'll also compute for each point the distance to its nearest neighbor, and then compute the average of that and the maximum. And what you will see is that now, if I increase dimensionality from p equals 1 to p equals 500, here minimum, maximum, and average distance will become more and more the same, and there won't be such a huge difference anymore between these three statistics. And also the same happens here for this average distance to the nearest neighbor and for that maximum distance. And there's also, for example, a quite well-known paper by Agarwal from 2001, where they discuss what that kind of implies for distance-based machine learning and data mining algorithms, so clustering techniques and classification techniques based on distance metrics, and what this implies for L1 and L2 based calculations. And the only thing I want to steal from that paper is this definition of a local contrast, because that fits nicely here with the simulation on the previous slide. So they are now kind of transforming these statistics just a little bit by computing here this relative difference between the range of all pairwise distances when they compare this to the maximum distance. And you can easily show that this goes down pretty quickly to 0 if you increase a dimensionality p, or it becomes quite small. And here we also specifically for KNN kind of invented here in this slide set a similar contrast definition, which we called here the contrast of locality, where we compare the average distance between pairs of points to the average distance to the nearest neighbor. And again, this goes down to 0 even quicker than this other guy here. And if you want to have like a similar or kind of like a slightly different viewpoint on what happens here in this calculation, in this formula, just divide this guy by this guy, and that will always be exactly 1, right, in this relative comparison. And then the only thing that is left here that's kind of interesting is here this direct quotient, minimum distance divided by maximum distance. And here what you have is average distance to the nearest neighbor divided by average distance between arbitrary points. And if the first term here in the sum is 1, and this goes down quickly to 0, what that must imply is that here for the second quotient, these two guys, they must become nearly the same, right? So that means the average distance to the nearest neighbor has become very, very similar to the average distance between arbitrary points in our space. And this is exactly what we don't want for local methods to work well in such a space like K&N. So we can summarize the consequences for our K nearest neighbor algorithm now as follows. So at constant sample size n, and when the number of extracted features p grows, then the distance between observation increases. And that means the coverage of the p-dimensional space decreases as well, and every point basically becomes isolated and far away from all other points. And that kind of makes local modeling in such a scenario basically impossible. So the size of our neighborhood, nk, that I need for a constant k also increases now. So I need more and more, parts, more and more local area in order to be able to cover in my nk neighborhood to cover k points. So at a certain dimensionality, my k nearest neighbor method is not anymore a local method. And even reducing k dramatically does not help me that much either here, because the fewer observations we now average, the higher the variance of our fit becomes, right? So K&N estimates get more and more inaccurate with increasing dimensionality of my data set. And to demonstrate this, I now generated a very, very simple artificial data set of dimensionality p as follows. So I guess it might even be easier to kind of directly skip to the visualization of this. So I picked two central points here. So I guess I call them mu and minus mu. And mu and minus mu have all of their feature values set to exactly a. And around these two center points, I'm now sampling from a simple Gaussian distribution with probability 50% from this guy and probability 50% from that guy. And I'm using a very, very simple unit covariance structure for my multivariate Gaussian. Okay, so univariate covariance structure, two Gaussians, one has mean vector a, and the other has mean vector minus a, minus a, minus a, minus a. And I've now defined a always exactly as 2 divided by square root in p. And why I did exactly this will become a little bit clearer in the next slides. So the reason for this is that for all of these data situations and different dimensionality settings p, the base error of my data situation is always the same. So I'm comparing fair situations among each other. So the base error is always the same for each dimensionality p. And in 1D, it would look like this. So we would have here our minus a and our plus a. And for 2D, it looks like this. And I will now prove through the next slides that the base error is actually constant and independent of p. So this is a little bit tedious here, so I will not read out every little, step of the derivation. It's not very difficult. I guess it might be somewhat instructive to see this in detail if you want to. So that it's really not that difficult, it just needs a couple of lines. So first of all, I will derive a formula for my base optimal decision boundary. So I can do this in this case here because I know exactly how my distributions look like, right? I don't have to estimate them from data because I know the simulation setup. I know how these, I exactly know how my data is jointly distributed. So I can now start here with this posterior probability of a certain x being from the positive class. I can use my good old friend, the Bayes theorem here, to turn this around. And now I can start plugging in stuff and simplifying things. So first of all, I know that, what do I know? I know that this prior probability is always 50%, right? Because I assumed that for the simulation. I have that, let me see. No, I'm not simplifying it any further. I'm now simply saying that I'm classifying now a point as positive if this guy here is larger than the associated term for y equals 2. So, I don't know, the point being in the second or in the negative class, I guess you could say. And now I can simplify this relation here by multiplying with 2, by multiplying with p of x. So, and then plugging in the formula here for the Gaussian for this cluster and for this class, and then simplify this even further. And at the end, what comes out of this is that I have this simple linear formula here for my decision boundaries. So my decision boundary is a hyperplane, and the orthogonal vector, the normal vector of that hyperplane, is simply mu. And this should be absolutely non-surprising to you, because what you're kind of doing here is kind of setting up a situation which is exactly the perfect situation for a linear discriminant analysis classifier. So you have two classes, and given the class, you know that everything is normally distributed, and you also know that covariance structure is equal. So that already tells you that the optimal classifier is basically LDA. And you even know a little bit more because the covariance structure is not only equal, but it's also completely unit covariance. You know basically that the can basically connect here these two mean positions, and then you know that here on the middle of those and orthogonally to this connecting vector, this is where your optimal decision boundary will lie. Okay, so tedious until here. Further, I guess, visualization of the situation. 1D, 2D, and this is what I now mean if I want to talk about the Bayes error. So these are the amount of points, or the probability mass of points, where even under the optimal model, I will still arrive at an incorrect classification at the end. So in a certain sense, you could call this the irreducible amount of error that's contained in the simulation setup. And of course, that's not zero, right? Because with a certain probability, you are sampling from this blue guy here, but you are still assigning a sampled point to this yellow cluster. So, and we can now also, at the end, based on this optimal decision boundary formula, calculate the corresponding expected misclassification error. So the corresponding expected misclassification error is a situation where we have sampled a point from class 2 and are still assigning this now to class 1. Or we are sampling from class 1 and assigning it to class 2. So, and that happens exactly in the case with 50% probability, where we assume that we are in the second class, and then here this, and now we are on the positive side on this hyperplane, or with 50% probability, we are assuming we are in the first class and we are in the negative half space with respect to this decision boundary hyperplane. And because of symmetry, we can easily now add these two things together and simplify this in this form here. We can now write out what this scalar product here means, and also plug in the definition of our mu vector. So this will be here this sum over a times xi, and we sum all of these guys up, and they should be less than 0. Let me check this last line here. And we can now also, of course, divide that whole thing here by the constant a, and then arrive at that last simplifying step. So now we can take a good look at this and see, because we know that all of these xi guys here, all of these xi guys, they are independent normal random variables, given that we are in class 1, because of the unit covariance structure that we know that goes on if we are inside of class 1. We can now, hang on. So what we know is that all of these xi guys here, they are all, like I said, independent normal random variables with mean value a and standard deviation or variance 1. We also know how their sum is distributed, given that we are in class 1. So we know here that we simply have a new mean value of p times a, and also the standard deviation here is, because we are under this independence assumption, simply also sums. So we have a new mean value of p times a and a new standard deviation of p. And because of this, this formula here is now a very, very simple calculation based on a univariate normal with this configuration. So from this, you can easily calculate what the base error is. So how likely this here is, depending on this specific setting of A. And you can now also, I guess, see why I chose this specific configuration of A, so that at the end, we basically end up with an independent formula or an independent constant of P. And the base error at the end will be something like 2% or 2.2% of misclassifications independent of dimensionality. Okay, so far so tedious. So I hope this was somewhat instructive to see these calculations, to see that this is actually possible to do something like this in these simple setups. What is now maybe more interesting for us here in terms of curse of dimensionality, I'm now going to train a KNN classifier. So not an LDA model on this simple situation, and I'll train this for various settings of k. So for k equals 3, k equals 7, k equals 15, and then increase dimensionality and monitor generalization performance. And because my data set here is, I guess, not super big in my simulation study, or, I guess it's also not too small, but I'm just going to be like extra careful in not introducing too much noise through the stochastic evaluation. I'll actually do a 10 times repeated 10-fold cross-validation. And you can see here what happens with the misclassification error if you increase the dimensionality in the setting from a few dimensions to 100, 200, 300, up to 500. Yeah, and up to 500, that's not a lot in modern machine learning applications. And you can see here that just for like 100 or 200 observations, the expected misclassification error for new independent test data has become already absolutely large. So it's beyond 10 or 20%. So for a situation which should probably, for a very, very simple situation, right? It doesn't get simpler than such a setup here in machine learning. That's actually absolutely unrealistically simple. And we should actually arrive at a model that has a prediction error of, I don't know, maybe something like 2.5 or 3%, but not 10 or 20. And this is here, this yellow line. So this is the base optimal classifier and doesn't really depend on K, right? So all of these different K settings, they could also try it out 20 or 1 or whatever. They all deteriorate very, very quickly with increasing dimension. And the reason for this is this kind of abstract discussion that we did here before, which we now have directly observed in a simulation study. Here is another example now with a linear model. So I'll now also have a look at how that behaves in a high dimensional regression setting. So for this example now, I simply take this well-known Boston housing toy data set for regression, which consists of 13 features which describe the Boston region. So for example, crime rate, state of the population, in order for me to model the average housing price in areas in this around that Boston region. And I will now train a linear model on my data consisting here of roughly 500 observations. And in order to make it really high dimensional, I'll now artificially create a lot of noise variables. So 100, 200 or 300 completely non-information carrying variables, and look at the performance of my linear model if I train on this modified data. And again, I'll measure expected generalization performance through 10 times repeated tenfold CV. And this is what happens with the performance of my linear model if I add more and more noise variables. And you can see that now my mean squared error increases to an unacceptably super high value, which I'm pretty dissatisfied with after adding these noise variables into the data set. So if I'm using this unregularized simple linear model, this begins to struggle quite easily with the added noise features and with the higher dimensionality of the underlying data set. And in order to compare this to an alternative model, I've also used a simple regression decision tree, or simple regression card tree. And you can see that this copes much better with the data situation. And at least for this added range of noise variables, mean squared error is actually not increased for the decision tree. And we can now discuss a little bit why that actually happens. So first of all, maybe let's start with the decision tree. So why is the decision tree not really affected by these added noise variables? So what the decision tree does is it iterates for each split point that it creates in the tree. When it grows the tree, it iterates over the features, and then it calculates which of the available features reduces risk the most when the tree actually splits on that feature. And that means as long as noise features don't look more attractive to us than real information carrying features, these will never be added to the model, and we kind of end up with a model that looks exactly the same as a model that would have been fitted on the lower dimensional data set with only the information carrying variables in the data set. So the noise variables don't even kind of enter the data set. They can enter the data set in a very extreme situation where just by pure chance, these noisy non-informative features actually just by pure chance begin to look better than an information carrying feature. That can happen if I would add a lot of noise variables here to the data set. But no, as I have said, or as you can see here from this example, you really have to go to a super high dimensional space in order for that to happen. So for the linear model, the situation is a little bit more complex, because if you think about this, you could say, well, maybe all of the features are active in my linear model. So if I'm now using 400 noise variables and 13 information carrying features, my linear model will also have 413 coefficients and active features in the model. But in a certain sense, you would expect that all of the coefficients for the noise features get estimated nearly exactly as 0, so they also shouldn't have any influence in the final model, right? So why is that problem then still here? And the reason why that happens is because the coefficients of these noisy features, they will not be estimated precisely as 0 in our unregularized linear model because of small random correlations. And when we add an increasing number of these noise features, prediction error rises. And we can actually look at this a little bit more in detail when we quantify the influence of our noise features now on the prediction of each iteration, or of each observation, I guess it should have said here on the slides. Sorry, I guess that's a typo. So let's simply decompose our prediction yi here for an observation I in the following manner. So we can kind of decompose this in the intercept, the part of the linear sum that is calculated with respect to the true information carrying features, and then the part of the sum where we multiply coefficient times feature value and then add that up for all of the noise features. And these guys here, or the coefficients here in this sum, each coefficient individually will be quite small and will be pretty close to 0. But you will see that these errors now can accumulate over larger sums for higher dimension spaces with many noise features. And at the end, if P just becomes too large, this thing here will basically dominate the prediction with respect to the information carrying features and kind of destroy the good effect of this guy here. You can see this by this simple comparison where I have simply now computed here the quotient of this y hat noise and divide this by y hat true plus y hat noise. Always taking the absolute values of these. And if you look at this here now visualized for different numbers of noise features added, so for example for 100, 200, 300, 400, what you can see here easily is that most of the time on average over 50% or over a large percent of the flexible part of the prediction, which is here this y hat minus the intercept, is actually determined simply by the noise features, which is a completely bogus part of the prediction, and of course cannot add anything valuable to the prediction, and basically will kind of shift it away from a reasonable value. So this guy here, or this guy, becomes much too large in comparison to this guy, while actually in an ideal world, this guy here would be nearly 0, right? Because all of the coefficients in that sum would also be super, super small. But because of these unfortunate accumulations, this strong increase in prediction error happens. So what are potential ways of guarding against these problems? So one thing we can, for example, do is we can simply kind of collect more data. That's of course not always viable in practice, but if possible, it's a really good idea. We can also kind of reduce the number of dimensions before training. We could use something like PCA. We could use feature selection, or something that's still valid in the new age of deep learning is really thinking very hard about what are useful features, instead of adding everything in there that could be of some speculative value. Just try to kind of think about your domain, figure out which features make sense, carefully kind of hand select them, and then work in this lower dimensional space. Yes, I know. Of course, we kind of expect ML to help us with this problem of selecting information carrying features. And of course, I will discuss how we can still work in general in these high dimensional spaces with ML models, and I'll also talk about feature selection here in this lecture. But if you have the option of reducing, making your life easier, because you have domain knowledge, you should definitely use that. And also, of course, regularization. I've mentioned this now a couple of times, and this is what we will discuss very, very soon in an upcoming subsequent lecture chapter.